welcome to this video on the road to quantum reality. This time we are going to look at the amazing and thought-provoking manner in which orbital angular momentum appears in real-wave quantum mechanics. And we will see that a massive rift opens up between real-wave quantum mechanics and the common interpretations of quantum mechanics, such as they are. We will find that while real-wave quantum mechanics can mimic the Schrodinger and Dirac solutions, it also describes features which are not present in the solutions of either of these two equations. In the past few videos, we have applied the principle of phase harmony to motion of structures through the ether. We showed that the real-wave quantum mechanics wave function can be factorized into a p, or phase wave, and an s, or standing wave. The phase wave is just the de Broglie matter wave, and its characteristics describe the momentum and relativistic mass of the structure. So we identified the role of the wave vector k of the p wave in describing the momentum of the structure via the de Broglie relationship P equals hk. And we showed that the angular frequency of the p wave described the relativistic mass of the structure. Our model in reaching these findings was of structures of FRs moving bodily through the ether. You might imagine that this is going to be relevant to finding the orbital angular momentum of structures by comparison of linear motion to orbital motion. But this is not so. Let's go back to our original findings for structures in a 2D simple harmonic oscillator potential. We found these as eigenstructures based on our interacting FR model, and we could compare their form and degeneracy behaviour with the quantum mechanics results. But when we looked closely, we could see that as well as the phase alternation, which we had previously seen and explained in the 1D case, we now had some additional phase variation across the structure. We also noted that some of the forms found by the eigenfunction calculation were superpositions of the pure states that quantum mechanics might suggest. In particular, the two structures in the second row appeared to be formed from linear forms suggested in sources such as the St Andrews site, and pure radial forms which might be expected to have orbital angular momentums, such as those described in, for example, French and Taylor. However, we noted that by multiplying each form by an appropriate complex number, i.e. weighting relative contribution and relative phase from each structure, summing and renormalizing, we could produce the pure rotational forms. And it is these forms which we need to study to evaluate if, how, and to what extent they encapsulate orbital angular momentum. Before we can do that, we need a quick review of how quantum mechanics handles orbital angular momentum. In this, I am broadly following the text by French and Taylor, An Introduction to Quantum Physics. If this is physics kindergarten to you, then maybe just focus on the assumptions and how they might be interpreted. It all falls back on the de Broglie relationship for matter waves, as so much of quantum mechanics does. We are envisaging a massive point particle in motion, with momentum given by the wave vector of some wave which quantum mechanics doesn't really have an explanation for, but for which we do. It is one factor of our solution with phase harmony. It is our p wave. In quantum mechanics, the name of the game is to find some process, which is usually described by an operator, which we can apply to the Schrodinger wave function to spit out the feature of the particle which we are interested in. For linear momentum, the operator is this one, which we have pulled out of a hat, but which we can demonstrate to be correct by applying it to a wave function including the e to the ikx as a factor, such as our p wave. Actually, there is a nicety here which is easy to overlook. We are sort of assuming that the only gradient in x results from the changing phase, that there is no magnitude variation in psi, which of course is okay for a free particle. But it is as well to remember that the gradient we want is the gradient of the phase. We want to operate on this function, which is just a plane wave with infinite extension, to see what we get. In other words, perform this operation by carrying out the differentiation, which is a doddle for the exponential function because we just bring out a factor of ik, and cancel the i's and recognise that hk is equal to p and that the bracketed term is just psi. So if we apply the linear momentum operator to psi, we get psi multiplied by the linear momentum p, which is just a number. So far, so good. Now, with the orbital model of orbital angular momentum firmly fixed in our minds, meaning we are envisioning something planetary, we try to apply the strict classical recipe for finding angular momentum, namely finding the cross product of the momentum of the particle at some instant multiplied by its distance r from whatever point we are calculating the angular momentum about. But we only have operators to give us the linear momentum, so we follow the classical steps exactly, using xpy minus ypx to give the z component, and we come up with this angular momentum operator, and similar expressions for the y and z components of the same angular momentum vector. But it seems like overkill to apply this three-dimensional approach because rotation is fixed in a single plane, which we can always assume to be the xy plane, and then the am vector will always be in the plus or minus z direction, with the plus or minus telling us which way the rotation is occurring. But if we are going to work in the plane, it becomes so much easier to use polar coordinates. And here it is easy to note that the problem of restricting the gradient to be of the phase is resolved if we can present psi as a product function between a pure function of r and a pure function of phi. Such wave functions have rotational symmetry with regard to the magnitude of psi. We are not going to worry about how psi changes its magnitude with r, only about how its phase changes with phi. In quantum mechanics, we are solving the Schrodinger equation, and we can apply the additional boundary conditions shown here. Without delving too deeply, we get the result that Lz is quantized in integer multiples of m, and the wave function is this. So, as far as quantum mechanical interpretation goes, we get this odd picture of fitting the de Broglie wavelengths around the nucleus, meaning somehow that when the massive electron is closer to the nucleus, it has to travel faster than when it is far away. Incidentally, this is exactly the pilot wave interpretation, which says the electron is a massive particle and it is guided by the wave to whiz around at the appropriate speed. Alternatively, the Born picture says that it is a massive particle, but the wave function is merely telling us probabilities for where it might be and how fast it is travelling, but in such a way that the orbital angular momentum is constant. Whatever the case, both interpretations rely on this notion of the gradient of the phase being related to the momentum, which we also showed for our linear momentum. Where does that leave real-wave quantum mechanics? We don't have a point particle. And even more difficult, it is not possible to have phasor harmony involving FRs moving at different rates depending on how far they are from the nucleus, especially because the inner ones have to move much faster than the outer ones. The distances between FRs will be continually changing. It's difficult to see how phase harmony could apply, and to be honest, I haven't even tried to do it. But we do in fact have a phase gradient, although it clearly has nothing to do with phase harmony in Doppler shifted waves. Maybe this is related to orbital angular momentum. Specifically, can we associate the gradient of the phase with a momentum? Well, no, because if you look at this structure, it is clear that there are significant phase gradients in areas where the amplitude is close to zero. If we tried to sum these as momenta, we would get an unlimited total. Instead, we might surmise that the phase gradient is telling us a velocity, because when we multiply each velocity by the FR magnitude, which we are considering as its mass, the sum would be limited because the total mass is limited. In fact, it's normalised to 1 in these figures. Incidentally, it could be argued that in the de Broglie P equals hk expression, the k is really telling us a velocity because the mass is assumed to be the whole mass of the particle. But for us, we are applying a lot of different velocities to lots of different parts of the structure. Anyway, let's give it a go. We can numerically calculate the gradient of the phase and multiply it by the amplitude squared. When we try it on the first structure, we get the following quiver diagram of the vector field. All the vectors are pointing to the centre. Odd, but we were not expecting any angular momentum in this structure anyway. We can in fact resolve the arrows into radial and axial components, and then multiply each axial one by its distance from the centre to get its contribution to angular momentum, and then sum them. And when we do this, we find that the angular component is vanishingly small for this structure, but there is some momentum towards the centre. Now let's look at a structure which we do expect to have angular momentum, namely the pure state obtained by combining complex multiples of the returned eigenstates. It turns out we can do this in two ways, and we get these two different quiver diagrams which look a bit like water flowing down a plug hole with clockwise or anti-clockwise spin. It's amazing, but even more amazing, when we sum up the axial momenta times the radius, we get that the angular momentum is plus or minus 1. Wow, might be time for a sanity check. We must always remember that we haven't knowingly solved the Schrodinger equation. All we did was to ask what form a stable, self-interacting real wave field might take subject to a simple harmonic oscillator potential, and the answer was these structures with well-defined internal phases. And treating the gradient of these phases as a velocity allowed us to calculate the correct values for angular momentum, exactly matching those from the Schrodinger equation. But we better just check the results for structures 4 and 6 when these are rendered pure. This time we get a bigger plug hole, but now the angular momenta come out at plus or minus 2. So that looks like great news for real wave quantum mechanics. It gives the correct angular momenta. But we have to ask, what is moving? These FRs are stationary relative to the structure. There is no backward and forward motion due to Doppler shifting. The answer I have come up with, and I stand to be corrected, is that for motion within a structure, we are looking at the flows of wave energy. In the relativistic 4 momentum vector, an energy flux is the same thing as a momentum because of the mass-energy equivalence. But if we are saying that the phase gradient is giving us a velocity for energy flow in the axial direction, then it must be doing the same thing for the radial components. The plug hole analogy seems to become even more relevant. We are seeing the flow of wave energy from the outer areas of higher gain, that is higher potential, into areas of low potential, from which it is presumably dissipated. And this has no apparent parallel in the Schrodinger equation. Our solutions have found something extra. Well, I don't know about you, but it seems to me that this area is ripe for much deeper investigation. It's physically interesting, as it seems to be matching the Schrodinger equation, but saying so much more as well. It also implies that much of the interpretation of quantum mechanics is ill-conceived. In relativistic quantum mechanics, it is often said that the Dirac equation incorporates the correction for the electron moving at higher speed when it is close to the nucleus. It is often called the relativistic correction. But such a thing does not exist in real-wave quantum mechanics. FRs are stationary. The mathematics of real-wave quantum mechanics is also intriguing. We haven't used an equation as such, but instead have applied this highly geometric convolution process via an eigentype calculation, and all these features just come tumbling out. I would love to understand it better, but I've been doing this project on and off for 35 years now. It would be great to see it through a bit further, but it needs others to pick it up and run with it. So why not get stuck in? In the next video, we are going to show that the theory extends naturally to 3D structures, although limitations on calculation means they have to be very small. However, they are big enough to show that the link to quantum mechanics remains valid, and they give us a remarkable insight into the origin of the exclusion principle and the nature of fermions. Please like and subscribe, and don't forget to tell all your physicist friends.